Assuming that the derivatives exist, there's actually nothing stopping us from taking higher and higher and higher order derivatives. There's no reason why we should stop at order 2. And this means we can very naturally define the nth order derivative as the derivative of the n minus 1 derivative. Mathematically, we can write that dn dxn is the derivative of the n minus 1 of f dx n minus 1. And specifically the second order derivative is just the derivative of the first one. If we really want to be specific and take this on board fully, then the first order derivative would actually be written as something like this. But we won't, because we know what it means. It makes it look weird. There's nothing stopping you from using it, but it just means you'd have to write more, and it doesn't really add meaning at all. We've already seen that this is in Leibniz notation. In Newton's notation, we use this for the first order derivative, then this for the second order derivative, third, and from then on we use Roman numerals. So f and then 4 in Roman numerals of x. This is the fourth order derivative, the fifth order derivative, etc. So if you want to use Newton's notation, this is what you'd use, and typically once you go above 3, you use Roman numerals. For Leibniz notation, you use the actual number of the derivative order. If we take an example that's in your lecture notes of the function f of x equals x to the power of 5, and you want to calculate the sixth, this is the sixth order derivative of f of x, you could very easily say it is 0, because you'll be dropping all the terms down, and then you end up with just a number, you take the derivative of it, you get 0. And if you were to calculate the fifth derivative of f of x, you'd see that you get 120. That is because you'd be multiplying 5 by 4, by 3, by 2, by 1. You'd get 120. And you could also try out another example that's in the lecture notes. That's e to the power of 2x, for example. And let's say for some reason, very odd reason, but some reason you want to calculate the 20th derivative of f of x. In this case, it's quite easy. All you do is every time you differentiate, you get the function back and then 2, which means you'd get 2, and then 2 gets multiplied 20 times. So that's to the power of 20 e to x. And as long as you understand the notation and Roman numerals for Newton's notation, and just using the actual number of the order of the derivative for Leibniz notation, you'll be able to take higher order derivatives. All you have to do is calculate another derivative and another one, and it is important to understand the formal definition of the nth order derivative being the derivative of the n minus 1. One thing that you could ask is, are there any applications of nth order derivatives? As a physics student, you probably already interpret, for example, the first order derivative of position as a velocity and the second order as acceleration. You may already know that the third order is called jerk. It's typically quite important in things like engineering and motion control. And the fourth order can be called snap, and it's useful, for example, for the cosmological equation of state. And in many systems, it is useful to go to higher and higher derivatives, but this becomes increasingly rare. The lower order derivatives are definitely the most used, but there's nothing preventing you from taking higher order derivatives, especially when functions are very complicated and are varying in very, very weird ways. As you've just seen, section 6 is way more compact than the big section 5 that introduced lots of rules and tools for differentiation. And if you've completed this list, you are now definitely ready for part or section 7, where we're going to have a look at all these tools, but now for functions of more than one variable, meaning, for example, surfaces, like what I'm doing to the lecture notes right now, and we'll be able to have a look at partial derivatives, essentially looking at the behavior of a function when we fix a direction, taking limits over surfaces, which is definitely fun, but not that easy, and also having a look of how we can write equations of surfaces, for example, a cylinder, and also how you can visualize them in a program which is called TopCat, and for which I provide a grid and very detailed instructions that you only need to copy paste, and then you can move it in 3D, and I'll try to demonstrate in those videos as well. So I'll see you for the next section.